Good evening. I'm Hussain. We are uh, delivering lecture on X-ray crystallography and solid-state chemistry lecture series, and this is the 24th lecture on structures of solids. Well, in the 23rd lecture, I finished with this slide, but I think we have to discuss a little bit more about these slides, and that's why this is the first slide. And then we continue with the other slides. Well, we are talking about various compounds, for example, let's say covalent, ionic, etc. compounds. So sodium chloride, for example, sodium chloride, aluminum oxide, sodium oxide, zinc oxide, etc. And we said in the beginning of the structure of solids that we can describe structure with the help of unit cell description. And then we say that also unit cell description is giving with concept about it, though it is very accurate, but that is, if we discuss the structure in other way, we get more detailed concept of it. Okay, and then we were talking about closed spec structure, and that was, we say, the hexagonal closed spec structure or cubic closed spec structure, and we also said about interstitial sites in these closed spec arrangement. Well, there are some cations which are often a bit larger than that of anions, and in that case, accommodating this cation, we expand the anion area. And that was termed by O'Keefe as eutectic structures. And if we talk about eutectic structures, then not only that, we have also a little bit of oversimplification when we are discussing closed spec structure, because we assume that our sphere is a rigid model sphere, which in fact it is not in ionic structure. And also we see that there are different sizes of ion. Exactly which size we are talking about, that also a drawback in describing this structure. Anyway, interstitial site, one more thing, that interstitial sites are not always occupied. We can see that one set is occupied, another set partially occupied, and a large number of anion stacking. And that what we are showing in this table. If it is a closed spec arrangement, and if it is an anionic arrangement and cubic closed spec system, we know that we have two tetrahedral sites and interstitial site and on octahedral interstitial. Say, for example, if we have this cubic closed spec arrangement of anion, in this case, let's say sodium chloride anion, and then sodium is taking the position of interstitial site, and in this particular case, all the octahedral sites are filled and tetrahedral sites are empty. That sort of structure, we call it sodium chloride structure or rock substructure. Similarly, if we take one of the tetrahedral sites occupied and rest all are empty, that means other tetrahedral sites and octahedral sites are empty, then we call it zinc blende structure, which is mineral name is sphalerite. Similarly, if we fill one half of the octahedral sites and 1/8 of tetrahedral plus and tetrahedral minus sites, we come up with the spinel type structure. And you see, next here, what we are seeing that we are only half of the octahedral sites and tetrahedral sites are empty. We get cadmium chloride cytostructure and so forth. If we go to the hexagonal closed spec arrangement and see that the anion sites are arranged in hexagonal closed spec arrangement, and then cation sites, if we take a cation and octahedral sites are all filled, we get nickel arsenide structure. tetrahedral side, one of the tetrahedral sides are filled, then we get zinc sulfides. And the zinc sulfides here is Urzite. It's the Urzite mineral. And so the others are like this. We can see that. So we will see that we will discuss some of these structures in details, but not all. For example, in the syllabus, we see that it's Roxel type, or we have to describe Roxel's type, zinc blende, Urzite, and antifluoride, calcium fluoride, and then olivine, perovskite. These sort of structures are, we will discuss a little bit details. We go to the next slides. Well, we are talking about, or we know that the term is used, the Diaz ratio rule. And that what is the Diaz ratio rule? But that rule can help us to predict the crystal structure of ionic compounds. And how we get the ratio? The ratio is that we take the radius of the cation and then divide it by radius of the anion, and then we get that is called radius ratio. And we can see that this radius ratio, if we get a value from maximum value 0.155, the ratio is this, then it is in one-dimensional structure and linear arrangement, and coordination number is 2. Here I don't give an example. It's, let's say the example would be hydrogen fluoride is one of the example for this type of structure, linear structure. And then if it is greater than or equal to 0.155 and up to 0.225 radius ratio, the two-dimensional we call the arrangement trigonal arrangement. Similarly, we continue up to 4.414, it is tetrahedral type, then 0.732 maximum value, 732 square type, and then 732 we can have also octahedral sides. And there are examples for this type of ionic compounds. And then if it is up to 1, radius ratio is up to 1, then it is a cubic type of arrangement. Here are the examples. And then if it is more than 1, we get a cubic closed spectrum arrangement, an hexagonal closed spectrum arrangement, what we are discussing now, and the coordination number is 2. Well, we go for the next slide. And then now is another way of discussing the structure. It's called space-filling polyhedra. We talked about unit cell description and then about a closed spectrum arrangement, and now we are talking about space-filling polyhedra that we can also use to describe the structure of solids, both ionic structure, covalent structure, and metallic structure, etc. So, okay, we have seen in case of packing spheres that estimate the efficiency of packing sphere, and we say this packing is 74.05% maximum, but in space-filling polyhedra, we cannot do like that, the space-filling polyhedra, the efficiency. Only what we can do, we can see the topology of the structure by space-filling polyhedra topology. And that topology is being used intensively and classified these polyhedra structures developed by Wales and others, which you can get from reference books. And now what we are doing, we are describing this sodium chloride structure with the help of this topology. That means how we know that the sodium has got octahedral arrangement, and chlorine also has got octahedral arrangement. So for octahedra, when it shares in different way, and we come up with a different type of structure. For example, when it is edge shared, all through the edge share, then we get sodium chloride structure. If 6 corners are shared, then we get rhenium oxide type 3 edges are shared, this type, and then 2 edges and 6 corners. Now you see that sharing is being, till now we are talking about sharing with one type of share, either edges or corners or edges. But now edges and corner together, and then we come up with titanium oxide structure. 4 corners only, then we come out with this sort of structure. If we take the polyhedra tetrahedra, we can also share corners and get this type of zinc sulfide structure. And 4 corners shared between 2 tetrahedra, in between 4 tetrahedra and between 2 tetrahedra, and then only silicon dioxide structure. 1 corner shared between 2 tetrahedra, we get this anion type of linkage. And then 2 corners shared between 2 tetrahedra, we get this type of chain or ring structure. That's what. Now, we were talking about polyhedra, so it could have tetrahedra, octahedra, trigonal prism, etc. Please do remember that tetrahedra, octahedra, trigonal prism, this is the motif, not the crystal system. It is not a crystal system, it is a motif. And we use this polyhedra and then we get crystal system, and we talk then about unit cell, etc. By using this sharing, we get enormous number of structure can be feasible. So at least theoretically, it is very interesting that you exercise these categories and real structure on the basis of this space filling polyhedra and find out the enormous number of structures like this. Okay, do we go for that? Now you see, when we share polyhedra, we can also find out the cation-cation distance as well cation-anion distance. Here is we are showing a tetrahedra, how it's shared. This corner sharing, this is a tetrahedra, you see? And this is another tetrahedra. So if we shared corner, and then the distance between this and this is equal to 2mx. This is x and this is m, you see? So 2mx distance between. If we now, this is the corner sharing, if we we'll make an edge sharing for octahedra, we say that this angle becomes 90 degree, and we can also find out the distance between m and, that means bond length between cations, and also we know the bond length between cation and anion. Here we are, what we are showing here, we are not showing any octahedra. What is this? Tetrahedra. This is a tetrahedra, schematic diagram of a tetrahedra. What do we, edge sharing of tetrahedra. That's it. The edge sharing of tetrahedra, we can find out also the distance between metals, this distance to this distance, and that is what geometrically we find this. Okay, that's what I describe here. It is in this table. In this table, this same thing is written here. Okay, now we come to, now we are talking about how we see the polyhedra build structure. You see, this is a sodium chloride structure, and very well known arrangement. We've discussed a detail about it, is it not? That how close specking is going on. The anion, that means chloride ion, are having close specking. Chloride ion, these are chloride ion, close specking, and then arrangement, and then we get octahedral sites. These are the octahedral sites of sodium. Alternately, this is the octahedra of chloride ion, and here is the sodium cation. Okay, so here we get octahedra of sodium. This is chloride ion, and here octahedra of chloride ion, and this is sodium ion. So, well, to describe this structure like this, we are talking about rock salt, zinc blend, which is named as sphalerite, and fluoride, calcium chloride, and antifluoride, sodium oxide structure. We can group this structure. Why? Because all of them are having cubic close spec arrangement. of anion or face-centered cubic lattice of anions, and then they only differ with the position of the cations. We can say octahedral, tetrahedral, and tetra- sites. That's what we showed in the slide number 2. How it is possible. So what we said in slide number 2, that it's a rock salt type of structure. We get a cubic closed spec structure of anion, and all octahedral positions are occupied. That's what we showed here. And we also showed the polyhedral arrangement. This is a polyhedra, octahedral polyhedra, and age sharing is possible for this octahedra. 2 octahedra, showing how the age shared is being done. Zinc blend, what we are having, this sulfide ion is the cubic closed spec structure, or face-centered ion, face-centered cubic sulfide ions. And then what we have, only one of the tetrahedral positions are occupied. Another tetrahedral positions and octahedral position are empty. In antifluoride, both the tetrahedral positions are occupied. Octahedral positions are empty. Now, this is antifluoride. What is calcium fluoride then? We see that calcium and ions, not the anions. Cations form the cubic closed spec arrangement or face-centered cubic lattice, and fluoride ions are in tetrahedral coats, and therefore this we call calcium fluoride structure. And we will say that the calcium is having octahedral arrangement, fluoride ion with octahedral arrangement, and the fluoride ion is having bonded with a tetrahedral arrangement in this structure, and therefore we maintain a 1 to 2 cation to anion ratio. Okay. Next slide. You see, if we have a general rule for coordination numbers. How it is, if we have a formula like this, A plus X, the coordination number of A and X would be Y is to X. That is what is common things. But for both rock salt and zinc blende, what is it? X is equal to Y. And therefore, each has got the same type of coordination number. And here, X and Y are not equal. Therefore, the coordination number could be 8 or even 4. Okay, these are the unit cell of this three structure, what we are talking about. A is the unit cell for the zinc sodium chloride structure. B is the unit cell for the sphalerite or zinc blende. A for rock salt, B is the zinc blende, and C is antifluoride structure of unit cell. These are the anion, and these red are the cation. We will see the coordination at atomic positions. This is rock salt structure and the unit cell. The atomic position is shown here, and you know that this is an oblique arrangement to sketch. I would say that we are sketching this in a plane parallel to or perpendicular to an axis, let's say A axis or B axis. In this case, it is C axis. We are sketching that atomic arrangement positions and throw parallel to C axis. This is the same thing. This is also what we are doing here. You see, we show the closed circles. Closed circles are cations. That is a closed circle. That's a closed circle. And open circles are anions. And from there, we can find out the coordinates according to the coordinates of the atoms or ions in the unit cell. And that what is shown here, the coordinate. We can see that there are two ways of describing the antifluoride structure. What is these two ways? We can have anion position. This is if the anion position old cell. This is the anion position, and anion position that is it is on corner of the unit cell edges corner, and also the center of the faces. So here the corner, this is the corner. We are filling this corner by the fluoride ion, and also the center of the faces, all center of the faces, these faces, this face, and this other face, and these faces. So that how we see. If it is the corner, then we get 0, 0, 0. If the faces, depending on which face, we are getting half, half, 0, the half, 0, half, and 0, half, half. But then if we take the unit cell, the position of the cation, we can also find out the position of cations here. So therefore, if we have cations in the corner of the unit cell, then we have these atomic positions, and others are the anion positions in the unit cell. That's what we are showing here. So in pair, we can say like this: both by using unit cell and the coordinates of the atoms or ions, we can describe a crystal structure. We can also describe by filling the octahedral position or interstitial sites and giving close packing. Also, we can describe by using polyhedra, space-filling polyhedra arrangements. Okay, that's what we discussed. Now we can see that if we have this table shows the compounds which are crystallizing with rock salt structure and also having its unit cell. We show it here. So you see that lots of compound having cubic unit cell, most of halides and hydrides of alkali metals. Halides, these are the halides of alkali metals, and hydrides of alkali metals. You see, they can crystallize with rock salt structure. Okay, and then we can also see that there are cation double valent divalent metal atom. This is divalent metal atom, magnesium, calcium, strontium, oxides of these, and then sulfides, selenides, and tellurides of these compounds could be also. So here you can see that many ionic compound can form this type of structure. Also, some other, the metallic, for example, titanium oxide. We have titanium oxide. This is metallic structure, and then titanium carbonate. This is covalent structure. So this is the table. Some of the compounds, inorganic compounds, which shows sodium chloride structure and their cell parameters given in this table. We take the next one. What we are talking then we will be discussing about zinc blende structure, that is fluoride structure. This is what this is the tetrahedral arrangement, and here are the face-centered arrangement A, B, C. This is these two layers A, B, C. If you remember, when we are discussing closed packed structure, we said if the arrangement becomes of anions of A, B, C, it becomes a the structure itself becomes a cubic closed packed. So in here is fluoride, which is a cubic closed packed structure, and more extended network. We can see here how the tetrahedra is being arranged. Okay, so we will see the arrangement. The tetrahedral faces are approximately horizontal here. This is the unit cell showing the polyhedra sharing of corner, how it is arranged. So here we have also some compounds with zinc blende structure with its cell parameters, and a number of copper oxides, copper halides, and you can see this boron nitride, boron phosphide, etc., boron arsenide, aluminum phosphide. These are the structure, and here are the unit cell arrangement of this structure. You can see. So here, this is what the way we describe the crystal structure of solids, specifically inorganic solids, and we will be taking calcium fluoride and antifluoride structure in the next lecture. Till now, thank you for seeing this 20 lecture number 24th. Up till we continue this with the next few lectures of more structures. You will see that we will talk about metallic structure, and we will also talk about covalent structure in future lectures. Thank you very much for today. Thank you so much.